For our next problem, 11x plus 6y equals 17 and 5x minus 4y equals 1. Step 1 says all of the variables are lined up, the constants and the equals, and that's already done, so that's great. We need to choose now which variable you want to get rid of. Neither of these are real convenient. We could get rid of the x's or we could get rid of the y's. What we're looking for is the least common multiple. So if we choose the x's, the least common multiple between 11 and 5 is 55. 55 is the first number that can be divided by 11 and be divided by 5. If we choose the y's, we're looking for the least common multiple between 6 and 4. The least common multiple between 6 and 4 is going to be 12, because 12 can be divided by 6 and 12 can be divided by 4. So I think 12 is better than 55, and so I think maybe picking y's would be the best choice. Another reason why y's would be a good choice is because we have a positive already for the positive 6 and a negative already for this 4, and they're already opposites, and we like that. We want them to be opposites. So step 3 says multiply the equations to make the coefficients opposite values. So the least common multiple between 6 and 4 is 12. So I need to make this first one a positive 12, and I need to make the next one a negative 12. That's my goal. In order to make the second equation, negative 4, into a negative 12, I'm going to multiply it by 3, because 3 times negative 4 is negative 12. I don't really have to mess with the negative signs because they're already opposite. When I multiply the 2, I have to multiply all the way across. Don't forget the 17. If you are thinking you might forget 17, consider putting the coefficient on both sides so that you don't forget to multiply the 17. That's a common student mistake. So 2 times 11 is 22 in the orange. 2 times 6, that's positive 12y, that's what we wanted. And then 2 times 17 is 34. In red, we have 3 times 15, which is 15x. On my orange equation, I forgot my x. I should have written 22x here. Please forgive me. Okay, back to the red equation. 3 times negative 4 is negative 12y, which is what we wanted. Yay! And then 3 times 1 is 3. Notice that we have the positive 12y and the negative 12y that are equal and opposite. That's what we wanted. We worked hard to get the positive 12 and the negative 12 to be exactly where we wanted it so that we can add the equations. When we add the equations, the 12y and the negative 12y add to 0, and they get eliminated. 22x plus 15 is 37x. 34 plus 3 is 37, which is really convenient because when I divide 37 divided by 37 is 1. So my answer for the x is 1. To decide what the y is, I'm just going to go ahead and plug it into one of the two equations. I'm going to choose the second one just because the numbers are smaller. So 5x minus 4y equals 1. But I know that x is equal to 1 already. So I'm going to plug that in. So 5 minus 4y equals 1. Minus 5 to both sides. That gets me negative 4y equals negative 4. And divide both sides by negative 4. And a negative divided by a negative is a positive 1. So my answer is 1, 1. Again, if you're interested in checking, you can. 11 times 1 plus 6 times 1 is 17. That's right. 11 plus 6 is 17. How about 5 times 1, which is 5, minus 4 times 1, which is 4, is also 1. So that checks out. So this does work. Again, checks are optional. Okay, on our last problems, we have the variables lined up, so that's already done. Step 1 is already done. Decide which variable you want to eliminate. They're both pretty small. Let's go with the y's again, because 2 and 4 are smaller than 3 and 6. The least common multiple between 2 and 4 is 4, because 4 can be divided by 2 and 4 can be divided by 4. So I want one of them to be a positive 4 and I want one of them to be a negative 4. Since this is already a positive 4, let's just multiply the first equation by something to make the 2 a negative 4. In order to make a positive into a negative, I'm going to have to multiply it by a negative. In order to make a 2 into a 4, I'm going to multiply it by 2. Go ahead and multiply that all the way across, even to the other side, okay? Negative 2 times 3 is negative 6x. Negative 2 times negative 2 is negative 4y. Negative 2 times negative 1 is positive 2. The second equation, I want the positive 4 to be a positive 4, so I'm not going to multiply that positive 4 by anything. Or if you must, you can multiply it by 1, or just think of it as bringing it down, because you're not really going to do anything to that, because I want this negative 4 to be opposite of the positive 4. Are they opposite? Yes. And how do we do that? Well, we creatively multiplied the entire first equation by negative 2 in order to force that positive 2y to become a negative 4. We're the ones that made that happen. So we know that when we add negative 4y plus 4y, that adds to 0. What we didn't know was we accidentally made the x's add to 0 too. Was that our fault? No, that just happened. We were trying to force the y's to be the same, and accidentally the x's were equal and opposite, and that also added to 0. So the whole left side is 0. On the right side, we have 2 plus 0, and that's 2. Whenever all the variables drop out, you can't solve for a variable, and so you know you either have a special case no solution or a special case infinitely many solutions. The way we decide is we look at this. Is this a true statement or a not true statement? Well, this is not true. So my solution is no solution. Okay. You could also just write that symbol, the 0 with the slash through it, which doesn't mean 0, it means no solution. Our last equation is probably the easiest one of them all. Notice that the 2x and the negative 2x are already lined up. They're already opposite. So all I have to do is add the two equations. Negative 2 plus 2 adds to 0. Uh-oh. Negative 4 plus 4 also adds to 0. And 1 minus 1 also adds to 0. So I tried to solve for y by eliminating the x, but both the x and the y eliminated. So that's either a no solution special case or an infinitely many special case. How do I tell? Well, I look at the remaining number statement. Is this remaining number statement true? Does 0 equal 0? Well, yeah, that's true. And because that's true, my answer is infinitely many. The way we write that is the set of all x, y such that one of the two equations, it doesn't really matter which one, and then close it with your braces. This is an infinite amount of solutions, all that lie on the same line. It's not an infinite amount of solutions for every single ordered pair. It's just the ordered pairs that actually lie on the same line. If I were to graph this, which I'm not going to, but if I were, the two lines would be on top of each other. If I were to graph the no solution, which again I'm not, because I don't have time for that, I would get two equations that are parallel to each other and they never reach. But again, I'm not going to do that right now because I already solved it using an elimination method. I'm just trying to relate it back to how the graph would look if you were to graph it.